I was just pondering some questions mostly today. I just got on this thing I've been asking other people in Hangouts for a while and haven't heard any real good answers or prompting kind of questions about till this morning about why it is that a helium balloon rises, because when you think about it, it doesn't make intuitive sense. So I'm going to kind of not go over all over the map to try to answer this and not really solve it. I don't think, but raise some questions, because there's a lot of bad arguments that go around on this topic. And so it all does tie together with the issue of gravity. But you can see here, I'm starting out with a chart on the different spheres, so-called, and this isn't really so much an Earth-shaped hangout as just a basic science hangout from the standard perspective, because you have to start with questioning the way things are. And so basically what started this little quest of mine was the idea that if you hold up a deflated balloon, you take it out of the package and you let it go, it'll drop, okay? But if you fill it with helium, it'll rise up, even though with the helium, it has more mass than just the balloon itself, okay? So you would think intuitively this should be heavier and it shouldn't rise at all. But especially since it's contained, the helium is contained. It can't interact with the air. It can't disperse. It's trying to, but it can't. So why is it that the balloon goes up? And it led me all over the place trying to answer the question, because I don't like to do just, pat answers. So what I came across first was the fact that the answer has to do with the volume of air being displaced. Okay, there's the mass of an object has a certain amount of other stuff that it pushes out of the way to exist. Okay, so displacement is pushing other things out of the way. Well, in this case, air. It's just like if you push something, like if you have a basketball or something, you push it underwater, it really pushes up hard against you because it's displacing something much heavier, and that heavier thing pushes back. So it all had this helium balloon question has to do with the volume of air that it's displacing, which is much more than if it was not inflated at all. So the pressure under the balloon, the air pressure under the balloon, is greater than what's above it. And so it pushes the balloon up toward equilibrium, basically, with the surrounding air. But as the external pressure on the balloon drops, because the higher it goes, you have less pressure, the internal pressure from the helium goes up. So if the balloon is allowed to keep rising, just, you don't hang on to it or anything, you just let it go, the helium will put enough pressure on the balloon to burst it. And at that point, what's left of the balloon will fall, and the helium will dissipate. It'll just scatter in all directions. So the reason helium balloons eventually deflate at ground level, you might be wondering, is because the helium atoms are extremely small and they leak out through the balloon skin slowly. So I think pretty much everybody knows that, but I think sometimes things need to be said just to make a point, and that is that this is a displacement issue. So helium is like any other gas. It has no shape or volume of its own. It tries to expand or contract to fill whatever may be containing it. Which way it goes depends on where the lowest pressure is, since nature seeks equilibrium. It's like heat goes to cold and so forth. So one way to increase pressure is to put the gas in a smaller container. Another is to increase temperature, since that causes the motion of the atoms to increase and expand in all directions. And I will give you a link in the chat for more reading on that issue about how gas behaves in physics. I thought I pasted it, but for some reason it's not letting me. I'm trying a different browser tonight. That was part of the reason I wanted to run, but it's not taking my paste for some reason. I don't know why. Oh, well, you'll just have to do without the link. But there was a thing called Mining Quiz. It was a mining site. I figure they're not doing theoretical physics. They're being practical, and it's not Wikipedia, but miningquiz.com. and /download/basicgasprinciples.htm. So sorry, I can't paste it. I don't know why. Anyway, you can learn about how gases behave. And then they had this little fun fact that I got from that site and another one, that helium is classified as a noble gas. It comes not from the sun, but from alpha particles emitted by radioactivity. A lot of people think helium comes from the sun. And then you have to ask, well, how do you catch it? They don't answer that, but it doesn't come from the sun anyway. It comes from the ground, from radioactive materials. And the most economical source is natural gas. So that's where they get most of the helium, because natural gas is found in these deep pockets underground that are sealed off. And so if there are alpha particles from surrounding radioactive ore, they get trapped in there. And so when you process the natural gas, you can extract through freezing and these pipes with very small holes in them that lets only the tiny helium atoms out. That's how they get helium. Okay. And then they, like I said, they freeze it and they put it into containers and all that. And there's a really long link I was going to post, but I can't do that. So you'll just have to ask me if you're really that curious. I don't think most people are anyway, but that's how they get helium. So what does that have to do with gravity? Well, first of all, we have to think about these things I've got up on the screen here, these shells that are around the Earth. And what you can see there is that there's different names. They have a sphere and a pause, a sphere and a pause. The pause is the boundary between the two. This one chart on the left has temperature ranges. You can see that as you go up, it gets colder, which anybody would know if you've been at a high altitude or in an airplane or anything like that. You can check the outside temperature and it gets very cold. But then you get into the stratosphere, it starts to go back and warm up. And then into the mesosphere, it gets really cold. And then the thermosphere, it gets really hot. So it's not uniform. It varies. And chart on the right, you can see that these are different miles or kilometers up in the air. I gave rough equivalents. The chart didn't have those by itself, but it shows you kind of what's going on in which sphere. And that the stratosphere is the highest hot air balloon, or not hot air, but a helium balloon or a weather balloon, whatever, goes. I think most of the ones I've seen footage of go to about 20 miles. So they're still well within the stratosphere. And then the mesosphere, as you get, I think they're trying to show rockets and things. I'm not sure what some of that stuff is. I think meteors and whatnot. And then up into the thermosphere. And you can see the temperatures down here on the left are, they're extremely cold, extremely hot, but they get way hotter than that in the thermosphere. I just didn't have the whole, have a big enough chart that showed how it can get up to like 3,000 degrees or so. Just as a side note, low Earth orbit, which I've got on the right here, that's way up above off the chart here, is about anywhere from 160 to 2,000 kilometers, which is near 100 miles to 1,200 miles. The ISS, supposedly, the average height is about 330 kilometers or 205 miles. So if you say it's about 200 miles high, you're in the ballpark. And that is well up in the thermosphere, but still in the thermosphere. And I'll get more about that in a minute. And I do have a link there on the page that you can see if you're really curious about that. But you have to look into what temperature is. And I will tie this all back to the gravity issue. But like I said, one of my purposes was to just show all the stuff I looked at when I was trying to answer this question about why the helium balloon rises. And one thing, and I went to some physics sites, I went to some debunking sites just to see how they view this stuff. And sometimes it's an easy way to get source material you wouldn't have thought of. And one thing is about temperature and heat. They're different things. Temperature is loosely defined as kinetic energy of particles. That is to say, if you've got particles of something and they're moving, you have a measurable temperature. That's why they say that in physics, the end of the universe is called heat death, and because nothing can happen because nothing's moving anymore. There's spent all the energy and wasted it as heat. So, but as far as what you feel as temperature on, how it feels on your skin, it's going to depend on a lot of other things, such as how much, oxygen is in the air, how much humidity. So if the air is thin or dry, it's going to feel colder, even if your thermometer would say it's actually warmer and you shouldn't feel that cold. I've been in very low humidity rooms, computer rooms back, a couple decades ago, when they had to, the average computer had to be in a very clean environment, and it really feels cold just because of the low humidity, and you get lots of static and all that. But anyway, that's the perception of temperature. But actual temperatures are the net result of heat absorbed minus heat loss. So it's what you've got left after there's been energy exchanges with the environment. And that also includes how much mass the object has and so forth. So in a vacuum, there is no such thing as temperature, because there's no particles. That's what a vacuum is. It's empty. But if there's an object in the vacuum, that can have temperature because it has particles. The only difference is how the energy is transferred is the thing. Okay. So the actual measured temperature of the layers of, these atmosphere layers is less important than what they're made of and what's in them. Okay. So for the entire Earth, the sun constantly radiates a tremendous amount of energy to it, but not all of the Earth at the same time. So Earth has time to expend some of the energy. But objects or people in the upper layers of the atmosphere are not absorbing and reflecting energy the same as they would in the lower layers. So you can't just go by what's going on here on the surface, what you can observe and repeat yourself. You can't just go by that. You would have to be in that environment, and it's a complex environment. You can't just, have a vacuum chamber. You can't just have some kind of radiation or whatever it is, because there's all these different spheres, so-called, that have different properties. You'd have to put something there. And the thing is that you would have to, that's the scientific method, is you have to observe and repeat, and you can't just speculate and calculate and guess and get close to it. If you really want to know how something's going to behave in one of those layers, you have to put something there and test it. But what interests me more about the gravity question is these lower layers, okay, the ones that we can get to. So you can see that as altitude increases, there's a decrease in stuff, in molecules and air pressure and humidity and all sorts of things. So since we know that a gas will try to dissipate into areas of lower pressure and temperature, shouldn't all atmospheric gases disperse out into the cold vacuum of space? Why don't they do that? It seems like an intuitive question that you would think, okay, gases dissipate and things try to go from heat to cold and high pressure to low pressure. What's keeping the atmosphere stuck to the Earth? The responses I've been able to find appeal mainly to gravity and the Earth's magnetic field. Now, most argue that in order for the atmosphere to dissipate into space, molecules of air would have to be traveling at escape velocity. So they're saying they're not going fast enough to get out. Yet if this is true, wouldn't there be an external layer where all that rising atmosphere collects? It's going up. That's what nature does. And yet it can only go so far because of the escape velocity. So why isn't there a shell all around all the other layers where all that stuff gets trapped? Okay. So especially since gravity becomes weaker with distance, you would think at least there would be this constant upflow of air and decreasing pressure at the surface. If everything's going up, isn't that reducing the pressure at ground level in the troposphere? Why isn't that constantly dropping? Now, a possible answer would be that since pressure is due to the quantity of molecules in a given area, then it would increase as it rises, and so it would fall back down. In other words, if it's being stuck here because of escape velocity it can't reach, what's it going to do? It's going to condense and get heavier and fall back down again, you would think. But this would be a continual process. So there would be a constant vertical air convection going on, which could be the engine of some weather patterns. But yet again, with that constant movement in both directions, it's trying to rise up, and yet then it collects because it can't escape and it falls back down. Why do we even have these discernible layers? Why are they so consistent? I mean, there's not a hard and fast line between them. Those pauses are really kind of gradual transitions, but they're definable and they have a certain height range. How is that possible? We've got this continual convection going on vertically because air is trying to escape, but it can't because it doesn't go fast enough, so it collects and falls back down. How is it that we still have these layers after all that? But all of this depends on the presumption of gravity, okay? The magnetic field can be detected and measured, but gravity is only an effect we observe and not a cause. Gravity is an effect, an observation, not a mechanism. Okay, we can repeatedly and predictably create electromagnetism. You know, we can create electrical fields. We know a lot about electricity and magnetism, but not so much gravity. So what causes gravity? Is it the Earth's rotation? No. According to Newton's first law, objects move in a straight line unless they're acted upon by an external force. So centripetal force is one such example, and I think I have a diagram there. You can see that this weight is representing, like, if you're swinging something around over your head, that weight is like your arm. Okay, your arm is above you, swinging the ball on a string above your head. Okay, so it forms a circle. You can see here, and the circle has a radius. The radius, whoops, I didn't mean to move that. The radius is from the center, because that's what you're swinging it around, to the edge, however long that string is. Okay, so that's a radius, and going around whichever direction doesn't matter. And there you can see the source for that link. If you bother, you can pause the video later and look at it. And so according to Newton's law, what's going on here, that ball, as you can see on the right, if you let go, it will go off on a straight line. Everybody who's taken a physics class has done this demonstration. It never fails. If you swing something around over your head and then let it go, it will go on a straight line. It won't keep arcing or curving. Okay, so what centripetal force does is acting like you holding on to the string. I mean, it's not acting like that. That is the force that is called, that's pulling back, keeping the object that's circling, keeping it circling instead of going off on a straight tangent. Okay, and the tangent, of course, you can see here, there's a right angle symbol. This is the center, goes to the edge, that's half the diameter, and the tangent is a straight line, which incidentally, that's a big issue when you're trying to look for curvature on the Earth and that sort of thing. This is a tangent, is if you took a rubber ball and laid a ruler on top of it, a straight edge, it would not be quote unquote level with the surface of the ball. That would have to arc around the ball to be level in that sense. But a tangent is an absolute straight line. And that's what objects will do unless there is centripetal force keeping them from flying off and keeping the motion angular. Okay, so it interferes, like I said, Newton's first law. Objects will go, if they're put in motion, they'll stay in a straight line unless they're interrupted. And that's what centripetal force does. It interrupts it because it's pulling it. Okay, so it should be clear that gravity is not caused by the Earth's rotation. Rotation tries to fling everything off the surface at a tangent. You see what I'm saying? It's not going to go straight out from this ball, or from the big circle here. It's not going to, if you let go of the ball, it's not going to go away from the circle. It's going to go at a tangent, at a right angle. See, if you're, again, on the left here, if you're twirling this ball around, you let go, whatever point you let go, say it's here at this arrowhead, it's going to keep going like that and not curve at all until it runs out of energy and gravity pulls it down. So that's how we know that it is not rotation that's causing gravity. I know that seems like a no-brainer to a lot of people, but a lot of other people it's not. They think that gravity is caused by spin. It's not. Okay, and this is, like I said, an easy experiment you can do to prove that. So rotation tries to fling everything off at right angles, but centripetal force keeps it from doing that. So it's interfering with Newton's first law. Okay, so if the Earth stopped spinning, there would be no change in gravitational force because it has nothing to do with gravity. All gravity does is act like a restrainer and interference of the spin. But if there's no spin, it has nothing, no effect on it. In fact, the formula for gravitational force only considers the mass of two objects at a particular distance. And of course, they add in the gravitational constant. But there's nothing about motion in that formula. Now, of course, if the opposite happened, the Earth were spinning, but gravity stopped, everything would fly off at a tangent. In other words, if from your perspective, standing on the Earth, if it had been spinning all this time and it suddenly stopped, you would go flying off horizontally out into space. You wouldn't go straight up from the ground. You would go across the ground in a straight line until you wound up in space, according to standard model. Okay, I'm just saying we have to understand their model as it is and what centripetal force is and what it has to do with gravity. It actually has very little to do with it. Now, earlier we noted that a magnetic field could act as a barrier, that if we know the Earth has a magnetic field around it, but is that what's stopping, is that what you have to get through for escape velocity? Well, maybe, but an external magnetic field by itself would not account for the downward direction of what we call gravity. In other words, it could be a container, but it does not explain why things go down, and not just air and convection currents. Everything wants to go down to the surface. So the atmosphere, along with every other object on Earth, is pulled in one direction, and that's the key to the whole density and buoyancy and all that stuff. There's a direction component to it that we have to deal with. Okay, everything on Earth is pulled toward the surface, and it settles at whatever level it will achieve a balance with, between the object and its surroundings. It will find its equilibrium, but until it does, it's going to go down. Why down? Why that direction? I mean, even like we said earlier about gases, they want to go in all directions. But anything that isn't a gas pretty much wants to go down. So whatever the cause of gravity might be, it's not a containing force, it's a directional force. Electromagnetism can provide not only containment, but also direction. So is that what caused the observed directional effect that we call gravity, what we observe as gravity? Now, somebody might object that only metal and magnets are affected by magnetism, but there have been experiments done that even living things like you've seen, there's video of a frog being suspended in a magnetic field and it can move around. Not very well, but it can move and live in that field. But air, atmosphere, isn't magnetic. It isn't particularly metallic. So how does a magnetic field contain the atmosphere? How does it act as a container? And why can't we detect gravitational fields the way we do magnetic fields? So nobody really knows what causes gravity. They can only observe that it happens, but they can't say what it is, what causes it. There's nothing in the molecules of any given mass that pull things toward its center. Unless you get down to the really tiny atomic level of really minute electrical fields like the van der Waals force that geckos use, for example, that they don't really, not all geckos have these microscopic suction cups that makes them able to walk upside down on glass and things like that. Some of them use this van der Waals force, which is messing with at the atomic level with the surface of the glass, and it's bonding. Don't ask me how it does it and undoes it. Nobody really knows. But anyway, there's a thing that at the very tiny level, gravity isn't so much of a big deal. Okay, but it's still electromagnetism in a way. I mean, every atom is supposedly an electromagnet. So it only makes sense that this is something that deserves more attention than it's gotten. And you can read, that's what Tesla was into, and Eric Dollard and Ken Wheeler and people like that, if you really want to know about electromagnetism. But the reason magnets as we know them produce a much greater force that we can observe than these little van der Waals forces is because their molecules are all aligned the same way. That's why they're magnets. And that's why you can magnetize like screwdrivers and things. If you want to make them magnetic, you get these magnets, you just draw the screwdriver through it a few times, and it aligns the poles of the little electromagnetic, atoms in there. And that's why it has a net magnetic effect, because you've aligned those atoms and they all have polarity. So if you align enough of those, you get a magnetic force. Now they can be pretty complex. I was going to show you another link. What I can, since I can't post those, what I'll have to do is just say, go to images, an image search, and look up a toroid, donut shape, basically toroid. Let me just type that in the chat. Magnetic fields. Do a search on those, and you can also do, let's see, what was the other one? Disk magnets. Look up those on images or whatever you want to look them up on. People have, you can take iron shavings and put them on a glass surface and put whichever shape magnet under it, and the iron shavings will align with the field, and it isn't always what you normally see as a bar magnet. So it gets pretty complex. But anyway, magnetism isn't always as simple as you might think. So there could be more to this than meets the eye as far as it affects, the question of gravity. What we cannot say is that the downward force we call gravity is a necessary component of a particular shape or motion of the Earth. It's a side issue. It's a distraction. When people try to say, well, the Earth can't be this shape or that shape because of gravity, that's irrelevant. You don't have to have a bar magnet or a disk magnet or a ball magnet or whatever it is to make a magnetic field that with certain properties. And even the Earth's magnetic field, if you look at what supposedly it is, especially on a flat map, it's confusing. You go to, you see all these lines going north-south, and then all of a sudden you get to a certain area and they're just every which way. So it could tell you something about the surface topography, but it not really that much, because the magnetic field doesn't have to follow the shape of the physical Earth. It has to follow whatever is creating the magnetic field, which could be any shape. So it's a side issue. It's a distraction. Like I said, the whole gravity issue is irrelevant to Earth shape. So arguments over the nature or cause of gravity will never settle any of those debates until anti-gravity devices are invented and made available to all the common people who can understand the basic concepts. Gravity's cause will remain a mystery. Somebody needs to make it consistent, repeatable, and something you could teach in school that would tell you how anti-gravity works. Until they do that, they don't know. Nobody knows on any side of an Earth-shaped debate. Of course, ancient people could navigate the seas and predict the movements of all the heavenly bodies with really great precision long before there were telescopes, computers, rockets, theoretical physicists. They just watched. They made observations and kept track of patterns, and that's how they could predict then. You just watch, the sun comes up at this time and goes down at that time, and then the next day it's a little bit different. And that's just observation and taking a lot of data points down. That's how you start doing science, and it's a lot of tedious work. So a lot of times, not always, but most of the time, you go into the ancient past, as far as anybody can tell, people did not so much concern with the mechanics of how this all worked as and dissecting it, as they did just, how can I use this, to plant my crops? How can I use this to cross the sea? That's what they did with these things in the sky. They were more concerned about practical uses than they were about, just knowing things for the sake of knowing them. Like I said, there's exceptions, but the point is to be a good scientist, and you don't stop with the first or most popular theory of what might explain everything. Everybody's always looking for a theory of everything, but you can't just stop at the first thing that kind of sort of works. But that's what the mainstream does. They take one theory that they're all pushing and they all agree with each other. They do their peer review of each other and echo chamber this and that. And everybody thinks it's the truth because no other possible solutions are allowed to be talked about. And that goes for any kind of a theory. You can't just brush it off just because it seems silly or primitive, or even worse, might threaten somebody's career. There are an awful lot of people who can't even entertain the idea of something different, some other, cosmology, because their reputation is built on it. Okay. So basically just question things. And if you're not always going to get an answer, it's like with this thing with gravity, nobody knows what makes it. Nobody knows why it goes to the surface of the Earth. And we can't say center because we don't know what shape, size the Earth really is. You can go around on the surface and go places and map it out and all that. And that's another thing about maps and models. A map is just how are you going to look for certain landmarks and distances and directions. And you do use a compass for the most part. You can use the stars, like I mentioned before about the ancients crossing the seas. And that's what maps will do for you. And they'll be accurate for different purposes. That's why they're different kinds of maps, but those are not models. And anybody who's done this kind of investigation will know that what I think it's 8 miles. That's been the maximum anybody's ever drilled in Russia or someplace like that. 8 miles isn't real deep. And I mean, as far as what they tell us the size of the Earth is, at least on the surface, we know it's pretty wide, got a pretty good diameter to it. But the thing is that nobody knows what's deeper than 8 miles. They don't know the shape of it. They don't know what's in the center. They assume that there must be a molten iron core that with the spinning of the Earth makes a magnetic field, but that's not a proof. You can't test it. You can't falsify it. So how can it be a scientific theory? You have to be able to falsify a theory, that is to say, develop a test to break it. And if it passes, great. If it doesn't, then you keep looking. But that's the thing, is with gravity or anything else, if you can't find the answer, you can't just, you can, but you can ignore it, but you can't let somebody say, well, this is the theory, therefore it's the truth. And if you disagree, we're not going to let you into our college or whatever it is. They don't know what's in the core, but they tell everybody in school that they know. They draw little cartoons of, the various different hotter centers and magma and all these things. But there's got to be more than one explanation because none of them work by themselves. That's all I know. So all I was really doing with this tonight is, this was something I just worked on all day. I looked up some sources. Like I've got really only these 2 pictures here. You can go search yourself for the different kinds of magnets, like I said. But mainly I wanted to try to tell you what at least I understand what gravity is, what it is not, what the spin of the Earth has to do with anything, why the atmosphere has layers, why it is that we don't have this continual, outpouring of all our atmosphere that should have, disappeared a long time ago, and why there's a direction. Because again, with density and buoyancy, well, I understand what's going on with that, but why the direction is the question. Why do things get denser at the surface? Because they're being pulled down to it. And if it piles up, it's just like if you pile up a stack of bricks, the one on the bottom is holding the most weight. This has got the most pressure on it. So the thing is that this is not explaining the direction of the buoyancy. It's not explaining the direction of the density. It's not explaining the direction of gravity. Nobody has explained the cause of it. We just observe that it is a thing. Just like we observe that magnetism is a thing, we just can't, other than seeing that the particles are aligned inside a magnet, we don't know why atoms have an electric charge. They just do. We don't know how this really works. The more you split the atom, so they say, And the more they look into, the finer and finer details of biology, the more questions are raised, the more complex it gets. And I think we're just seeing the limits of human understanding. But the thing is that when it comes to the gravity issue, I'm just hoping that this little talk has at least given you some idea of what bad arguments to avoid, and that there are some good, you can learn from some of these other sites that are always trying to, sing the party line. And yet, if you know what they're thinking of and what makes sense to them, then you can talk to them, because even they among themselves, when they think nobody's looking, will ask questions that they can't answer, or they come up with some ridiculous responses that even people who want to believe the mainstream are having a lot of trouble with. And I think that's the place to start. If you're going to come up, try to convince somebody of a new idea, first you have to tell them what's wrong with the old idea. And then there's a vacuum that nature hates. Then they'll be open to hearing some better explanation. But the first thing you have to do is create that vacuum. And that's what this kind of a search will do. So I don't know if it answered any questions about helium balloons or atmospheric layers or magnetism or anything else. But this is just the thought process I went through when I was faced with a question that did not have a simple, intuitive answer. And I wanted to know why things worked the way they did and try to play it back as simply as I could. I'm not pretending to be an expert on any of this stuff, but the information is available if you want to look at it. So let me take a look at the chat. I'm always surprised when anybody shows up. Thanks all for coming. Let's see if there's any questions or anything. Yep, down with gravity. That's just a phrase I've been using. I thought it would be a good hangout title, but still a bit new. That's fine. I mostly do Bible stuff, but every once in a while I do something sciencey. I do have a cosmology playlist. The one on the sun, challenging standard cosmology. The sun is a good one for just raising questions on how the sun does what it does. It has 4 different motions, and they've been consistent by observation and not just by me. So, and I ruled out camera tricks and all that. So you might want to look at that if you're into this sort of thing. Let's see, anything else in the chat? Yeah, as far as water, the thing is that a lot of people, and here we get into the bad arguments again, a lot of people will say that, the water is massive and how is it that water can be held down by this powerful force of gravity, but a butterfly can fly over the water and not be affected? But here again, we have density of the water. It's much heavier, tight. The molecules are very tight together. It's heavy because of the downward force on that much mass in that much space. Whereas the butterfly doesn't have much mass at all. And it is much closer to the far lower pressure of the air. And so it gets complicated, but I don't have a problem with it when you do study the complicated math behind it and everything, and the physics behind it. And for example, a lot of people don't know why airplanes work the way they do. Well, what's going on, if you know the shape of the wing, it's flat on the bottom and has an kind of an arced surface on the top that tapers back. That's because when you move that shape through air, the air on top has farther to go in the same amount of time. And so it has, when it's moving faster, it has less pressure than the air underneath the wing. And so that's where you get lift. The air underneath pushes up on the wing. Okay. It has not as much to do with the mass of the airplane as it does with the fact that air pressure is lower when the air is moving. So just little things you can look up, and it's not all a conspiracy. There's some basic stuff. I mean, people have to know these things have to work or they couldn't fly at all. And, there are other things, though, that don't make sense. And so you won't know which is which if you don't first look at what the standard teachings are, and then you can ask questions and see if you can find some satisfactory answers. And like I said, with this gravity question, I couldn't really find any satisfactory answers because nobody really knows what makes it work. It just does. It's predictable. You can calculate forces. It's just like with that feather and hammer on the moon thing. The reason that throws people off is because the hammer and the feather will drop at the same time in a vacuum, but the hammer will hit with a lot more force. Okay, force is mass times acceleration. So if they're both being accelerated the same, and one has more mass than the other, they'll hit the same time, but the hammer will hit with a lot more force. And that's the difference. It's not intuitive, but these things are not tricks, okay? They're not all tricks. Some things are. Some things are bad logic. Like I always said, bad logic makes bad scientists. It's like conclusions that people draw that they don't ask enough questions, or they don't go, far enough back to a source of something. So that's really what real science is about, instead of just being ideologically pure, according to the people in power. Let's see. Yeah, gravity is a handy word to describe what we're observing, but it still is an effect and not a cause. That's the point. But it has a direction, and that's what density and buoyancy have to deal with too. Let's see. Anything that weighs a lot will not float because of more mass in a given area compared to what it's displacing. And that's the key. That's what was answering the balloon question for me, was how much volume of air is being displaced by something that weighs a lot less than air. Let's see. Theoria Apophis is this channel. That is Ken Wheeler, also known as, at least used to be, Angry Photographer. It's hard. He's hard to understand. He goes so fast and says a lot of words that just like, wait, I want you to stop and define those terms. But he and Eric Dollard, they're both way out there on electromagnetism, and one of my degrees is in electronics, and I'm still like, how much of what I learned was not entirely accurate, but it works. The standard teachings on electromagnetism are workable. You can use those to do things. I'm not saying it's the end all be all, but it is a practical science thing. It's an engineering thing. And so you can't just throw that all out, but you can say, okay, I think we're missing something because we're pretty sure somebody has anti-gravity devices, UFOs or whatnot, and they're not telling us about it. So that's what I would call a healthy skepticism, as opposed to a completely paranoid, everything is wrong, everything is bad, being afraid of your own shadow kind of skepticism. Let's see. Yeah, if you trust, this place is created and you trust the one who made it, then it'll all be explained eventually. Let's see. Well, that chat keeps, as soon as you get near the end, when you're scrolling, you've been scrolling back in the chat and you're trying to catch up, it jumps on you when you get close to the front. Let's see. Plasma in the center, like a mini sun, is possible, but we're just guessing because we can't examine it. We can't go down and take a sample. Yeah, Joshua 10:13 about the sun standing still. It seems pretty impossible with the standard cosmology, because even though, like I said, if the Earth didn't spin, you wouldn't know it, because we have this downward force still. But the thing is that's a really, that's the least satisfying explanation that the Earth stopped spinning. I mean, because gravity notwithstanding, a change in angular velocity you would certainly notice. It's not because of a lack of gravity, it's because of a lack of motion that you had been doing, and suddenly, you hit the brakes and the sun stands still. How does that happen with nobody on Earth noticing? I don't see how that's possible. And it's not an allegory. It's in historical genre. So people can take that how they will. I know how I take it, but that's a pretty strong rebuttal of the standard cosmology, the heliocentric. It's at least geocentric. Let's see. Anything else in the chat? Your sun is anomalous last year or so. I'm not sure what that means. Troposphere is the lowest level, the level we are in. The highest density, because it's the closest to the Earth, where everything else on top of it is sitting, even if it's not technically weighing that much, it's still all stacked up. Hard to say how much a cloud weighs, but thing is, somebody was trying to tell me clouds are gas also, but the thing is, clouds are water droplets that form around particles of dust or other things in the air. That's how they do cloud seeding. They put the particles in the air so that the humidity suspended, the water drops suspended in the air will congeal around that and form bigger drops of water. And eventually they get heavy enough to fall because of, again, the amount of mass in a certain amount of space. And it gets heavier than the air around it. That's why it rains. But it isn't strictly a gas. I mean, you can take half a definition. It's like cherry picking. People cherry pick the Bible. They can cherry pick science documents too, and they trip people up. Anyway, yeah, there's the level again. We have these level of troposphere, stratosphere, etc. Why do they have levels? I mean, it has something to do with why there's such a thing as the cloud deck. Let's see. In Genesis says sun and moon in the firmament. Yeah, because that was a question I used to ask back. I don't know. Gosh, I was probably in my late teens, early 20s. You'd read Genesis 1 and go, wait a minute. The sun, moon, and stars are in the firmament, and there's water above the firmament. That, the best I could come up with at the time, all those years ago, was, well, maybe there's ice. The water out there, beyond the stars would be frozen. And maybe that's where comets come from, because we're told that comets are balls of ice. Of course, not even, the atheists believe that anymore. They're not balls of ice. But the thing is, I was trying to make sense of waters above the firmament, which even after the flood, passages of scripture from above the flood will tell you that there's waters above the firmament. But the sun, moon, and stars are in the firmament. And so, what do you do with that in the standard cosmology? It just doesn't work. And then you have to decide whether you're going to take it as written or allegorize it, which gets you in a whole lot of other trouble. So I don't recommend the allegorizing view. Let's see. Could be question, but I have yet to comprehend. Of course, they are in the firmament. But yeah, that's the thing. It's a real problem for trying to stuff the Bible, stuff Genesis into standard cosmology, because it doesn't work, especially the order of creation, light before the sun and so forth. It doesn't add up. So let's see. Yeah, I'm pretty sure the government does have anti-gravity vessels of some sort. Not sure whether they're actually living things on those, though, because I'm thinking that if you have a strong enough magnetic field to do what those ships do, that you're probably doing really bad things to the brains of any sentient beings inside. I don't know. I'm just a guess. All right. I think that's all I had to say. And thanks for stopping by, and we'll see y'all later.